This video will discuss sp2 hybridization and polyatomic bonding. So our model molecule in this video is going to be BH3 borane, which has a trigonal planar geometry to it. All of our BH bonds are 120 degrees away from each other in the XZ plane in an equilateral triangle. So as I mentioned here, our molecule is in the XZ plane. So when we look at our atoms here, we have 3 hydrogens. Each of them is contributing 1 electron to the molecule, and those valence orbitals that they provide are 1s orbitals for those hydrogens. Our boron has 5 electrons. 2 of those go in the 1s core orbital, and then 3 of them are in the valence shell at the n equals 2 level. So we have the 2s orbital, we have the 2px orbital, and the 2pz orbital, both of which are in the plane of the molecule, and then the 2py orbital is perpendicular to it. Okay, so this means that our 2py orbital is going to be orthogonal to our 1s orbitals here because it's equally above and below the plane, so any overlap that would be formed on one side would be canceled on the other. So it's orthogonal to all of these hydrogen orbitals, so it is going to be a non-bonding orbital. Our 1s orbital on the boron is going to be occupied and being a core orbital. As we mentioned, it's much lower in energy, much more tightly held close to the nucleus, not ready to form any kind of strong overlap with our external atoms away from the central atom. We have our other 3 remaining orbitals on our central atom. We have the 2s orbital, the 2px, and the 2pz. And these orbitals are going to combine to give us orbitals which are oriented optimally towards our exterior hydrogen atoms and orthogonal to one another. So the way that's done is indicated on the left here. These are all going to be sp2 orbitals because they're going to be 2 parts or 67% p and 1 part or 33% s, giving us an overall sp2 type orbital. The first one we're going to have is we have 1 part 2s and 2 parts 2pz orbital. So that's going to give us this type of orbital here, where it's going to extend towards this hydrogen on the right. We have an orbital that is in relative sense here, 2 parts s, 1 part p, negative 1 part pz, and positive 3 parts px. That's going to give us this orbital here pointing towards this hydrogen. And the last one has coefficients of 2 parts s, negative 1/6 pez, and negative 3/6 px, pointing down towards this hydrogen here. So if you compute the overlap of these orbitals, all of them are normalized, all of them are orthogonal to one another, and they all form an optimal orientation towards one of our given external hydrogens. So just as in the sp case, we have either positive overlap, building up of electron density, constructive interference, and net bonding going on in our bonding orbitals, or we have the constructive interference, depletion of electron density, nodal plane going in between our nuclei, and antibonding forming between them, depending on whether they're adding together constructively or destructively. That's going to allow us to form our complete set of bonding orbitals here, where we're going to have our 2 electrons in the 1s core orbital, and then of our 6 remaining electrons, there are going to be 2 that are in a bonding orbital between this 1s and this sp2, 2 that are in bonding orbital between this sp2 and this 1s orbital, and 2 that are in a bonding orbital between this sp2 orbital and this 1s hydrogen orbital. So overall, we're going to have 1 net sigma bond forming between each of our BH pairs of atoms there. So this is sp2 hybridization. That's appropriate whenever you have a central atom with 3 external ligands combining 2 of our p orbitals and 1 of our s orbitals in a planar way to get net bonding in a trigonal planar type geometry.